Thanks for the generous introduction. So I'll talk about condensed matter physics, but in particular the modeling of solids, which has had an impact on science and other areas of science, and also technology. And I'll start by saying a little bit about science and technology because we're having some difficulty in my country supporting basic science. And it may be in other parts of the world. And the problem is many people feel that you should be doing applied science. There's nothing wrong with applied science. But the question is, what would be a good compromise? Also, I apologize, some of the things are elementary. So for those of you who are experts, you hear things for a second time. And also, I repeated a few slides from a talk I gave in about 3 years ago here in Paris. But I'll tell you a story about Felix Bloch. I invited him to Berkeley to give a talk. He was at Stanford. And he said, no, I gave a talk 2 years ago. I said, oh, we want to see you. So he came, and he started his talk, and he said, many of you are going to hear something that I said for a second time. But my good friend Heinrich Casimir told me, never underestimate the value of hearing something twice. I thought it was a good line. And that summer, we had a meeting in Versailles. And it was when the new high-temperature superconductors came out. And I had just given a talk at Berkeley on this. And my colleagues from Berkeley were in the audience. So I repeated the story of Felix Bloch. I said, don't underestimate the value of hearing something twice. At the end of my talk, this man who I'd never seen before came up to me. He says, I'm Casimir. I never said that. And then he went on for a half an hour asking me about everything that happened in superconductivity since he worked on it, oh, I don't know, maybe in the 40s. But of course, a brilliant man, and it was a great experience. So the most famous statement about applied versus straight science. Are you okay? Can you see? Okay. It was when Gladstone, who was first the finance minister and later became the prime minister of England, said to Michael Faraday, but what is the practical use of electricity? And Faraday said, I don't know, but someday you may tax it. And the point is that when students ask whether they should be doing applied science or basic science, the answer is the same as when the student asks if light is a particle or a wave. The answer is yes. And their influence is both ways. Of course, basic science is developed because of problems in physics, let's say, and that you're trying to solve, but eventually things happen, like, for example, the laser. I remember the first applications of the laser that I saw, and Charlie Towns was at Berkeley, and we talked about the early days. I was a postdoc at Bell Labs, as you heard, and we used to have the visitors wear a white shirt and a black tie, and they had a laser, and they would walk across, and it would cut, the tie would fall down, and they would go through, and the shirt was fine. And it was a big joke, and that was the only application. And so things change from basic science. So in the United States, probably the most famous scientist coming from the United States is Benjamin Franklin. And it's a good example. For example, when he studied lightning, the famous thing with a kite, it led to the lightning rod, which saved many buildings. But I was surprised that he also, in addition to all these inventions that he had, bifocals and many other things, he also was the first person to classify electrical components as positive and negative, and conservation of charge. And it was really curious that he supported Huygens. He and Euler both supported Huygens for the wave theory of light, whereas most people believed that Newton idea of corpuscular. Of course, now we have a deeper understanding. But of course, the final decision is always made by experiment. I apologize to the theorists here, but the experiment always makes the final decision. And of course, the wonderful experiments of Young with light showed that light had a wave nature. It's also interesting that Franklin was working on electrical conduction of bodies and seeing how the heat affects it. And this was also a problem that Einstein worked on, which is interesting. Now, it's not just the government that is talking about applied things. Around, let's say around the year 2000, there was, of course, great respect for Einstein, and there still is in the United States. And Einstein, for Time magazine, was the man of the century. And they felt that people who think should be well recognized, and they should be the elite of modern society. But now, if you read the kinds of articles that are written by intellectuals in the United States, many of them are saying that the true elite of modern societies are the engineers, the mechanics, and artisans, the masters of reality, not the big thinkers. And so these articles actually influence the allocation of resources. Now, of course, we need engineers and we need people who do these things, but we also need people to think about basic science. So I am giving you a commercial here, but it's one that you probably is well received. But if you read these articles by very intelligent people, they are pointing in the wrong direction sometimes. So in condensed matter physics, we are in a very good position because, like Franklin, you have both the attributes of the masters of reality. We're dealing with real systems, and the systems are sometimes very useful, devices and so forth. And also, there are very fundamental things that come out of condensed matter physics. So in a sense, this field rivals chemistry in its usefulness and applications, and its contributions to basic physics are often at the forefront. I'll mention a few things later. And so to just say a little bit about condensed matter physics, it's the largest branch of physics, 1 foot in fundamental, 1 in applied. There have been, depends how you count, but about 28 Nobel Prizes in this field. But one of the nicest things about condensed matter physics, which many of my colleagues maybe don't appreciate because they try to argue for the field like the particle physicists do. Particle physicists can write down maybe 9 fundamental things that everybody should work on. And then they build the machines for those things. We can't. But we try. So people say, well, it's very important to do high temperature superconductivity, this and this and this. And we shouldn't, because one of the main things is the diversity. Because condensed matter physics focuses on sizes of energies and distances and times that are sort of in the middle between the extreme astrophysical and, let's say, string theory, because we're in the middle, we can connect up with many other fields in engineering, biology, and chemistry, and so forth. So in a sense, it's argued that the diversity of condensed matter physics is because it's in this so-called Goldilocks region of sizes and times and so forth. Now, Einstein made a lot of proposals along condensed matter physics for his thesis. And it's interesting to follow some of these through. Now, the first one is he made a proposal for a thesis to measure the velocity of light using interferometry. We all know about that, to Professor Dr. Weber. And Professor Dr. Weber said no. He rejected it. So he went and he proposed the same thing that Benjamin Franklin was, let's look at the effect of heat on electrical conductance. And he went back to Weber. Weber said no, rejected. So he performed some theoretical work on the thermal conductivity, and he wrote it up as a dissertation. Weber said it was the wrong kind of paper. He didn't like it, so no thesis. So he went to see Professor Kleiner, and he wanted to talk about how looking at intermolecular forces from liquids to gases. Very interesting for condensed matter physics. You start with atoms that are far away. You have a gas. You bring them together. You form a liquid and form a solid. But Kleiner, I don't think Einstein realized that the professors talked to each other. And probably Weber told Kleiner that Einstein was a troublemaker. Anyway, Kleiner said no. So he then, unfortunately for Kleiner, he proposed the ideas that led to E equals mc squared. He wanted to look at Maxwell's work and for electronic properties, electrodynamics of moving bodies. And Kleiner made a mistake because that could have been the Kleiner-Einstein equation. Kleiner said no. So you have to be sensitive to your students, okay? You have to be careful. And so finally, he performed theoretical work on measuring the molecular dimensions of sugar molecules. And he wrote it up as a dissertation. He gave it to Kleiner and Burckhardt. And they said it was too short, 17 pages. So he added one sentence. And they accepted it. And finally, in 1905, this was his thesis committee. So it wasn't so easy even for Einstein. But it's interesting, the breadth and the idea of things that you might think would be more applied and things that you might think are more basic that he looked at. So in 1905, during the great year of Einstein, the molecular dimensions was an important part, and Brownian motion, and of course, special relativity and the photoelectric effect. But the point I want to make here is he often started with empirical models and then developed them into, or Gedanken models, or worked with experimental data. And then later, they became ab initio first principles models and refinements. And we see that throughout physics. In particular, the photoelectric effect. It was called a heuristic theory. It was a theory in which he was arguing, hand-waving. He did the calculations, but it was not a complete theory, and yet it was so important for the development of quantum mechanics. And even if you think of relativity, Poincaré certainly knew more mathematics, but Einstein had this insight of looking at empirical small models. Well, for us, the idea of the material, matter, being made of atoms was so important. And around the time of, let's say, 1900, it was not clear that there were so many people who didn't believe in atoms that these experiments and these theories were very important. So if you look around into science, you'll see that probably the most important concept in science is that matter is made of atoms. And of course, we know that the modern model of atoms is the quantum mechanical model. And on the other hand, again, I'd like to say that empirical model, like the Bohr model, was extremely successful and very important in developing the ideas of how atoms work, and had an enormous impact before full-blown quantum mechanical theory came through. And so there's this famous quote from Dirac that said, this was in 1929, that once they developed quantum mechanics, the underlying physical laws necessary for the mathematical theory of a large part of physics, like condensed matter physics, atomic physics, cold atoms, and the rest, and the whole of chemistry are thus completely known, and the difficulty is only in the exact application of these laws to equations much too complicated to be soluble. And many of my colleagues in particle physics used to quote this and say, well, you know, it's just applications of quantum mechanics. And Dirac was saying the rest is chemistry. But in fact, they didn't read the second part of what he said. This was his challenge. He said it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to explanations of the main features of complex atomic systems, like, let's say, solids. So we have quantum mechanics. And so the question is, How do we apply it? What are the models? Now, it's an interesting, I'm going to tell you about two different models. And the second model I'll tell you about comes back to Berkeley. Berkeley started here in Paris. He was a mathematician. And for those of you who are not familiar with him, he was slated for a very good career in mathematics. But then he switched to thinking about physics. And he argued with Einstein, saying that he didn't believe in special relativity, but Einstein convinced him. They had many arguments. There's still interesting aspects of Bergson's question about how you measure time that I think may still be open. So he switched from that to philosophy. And you'll see that some of the modern ideas about emergence go back to some of the ideas that he had. And he later got a Nobel Prize in literature. So he's the kind of person you'd like to bring to a cocktail party because he knew everything. And his point was that how you learn about anything about nature, let's say you're an experimentalist, or how in general you learn about nature, is through your senses. Seeing, hearing, touching, smelling, tasting. And in most cases, what you do is you probe a system, and then you look at the responses. So for example, if you look at light, then you see it. Vibrations for hearing, you raise the temperature, it gets hotter. Air for smelling. And experimentally, if you want to probe a solid, many of you are dealing with optics, you shine light on it, you measure what comes back, what goes through, and by measuring reflectivity, you start to get a theory of what's going on inside. Now, the arguments that came up about this is that Bergson would have claimed that's all you can know. And then you make models for what went on inside. And I'll show you what I mean in a moment. If for example, if you're here, I have a probe, which is just a hammer, it makes elementary excitations, and then there's a response function. So if this is light, you could be exciting all kinds of things inside, for example, phonons. And then you would have reflectivity. If it was a magnetic field, you'd have the susceptibility. If it was heat that you changed, you have the heat capacity. So there's a response function. And so the goal of theory in modeling solids is to produce a response function that explains the experimental measurements. So the two theories, the two fundamental theories in condensed matter physics that explain or tell you about what you know about solids or predict are, the first one is focused on the building blocks, interacting atoms. Putting atoms together, they interact, and then you explain the properties. And most of the work is there. The second one, called an elementary excitation approach, focuses on the responses. You look at the responses and try to explain. I'll try to make it clear. Now, both methods are important, and their applications have a tremendous effect on technology, and the concepts have greatly influenced science and technology. So for example, the most popular standard model of a solid is an interacting atoms model. One that I said Einstein worked on. You bring atoms close enough together so they interact and give you the properties of the solid. Now, you know what's going on inside. There are electrons and nuclei interacting via electromagnetic interactions. So a typical picture that you have is, this is not the correct structure for silicon, but let's say it's silicon for a minute. You have the nucleus, which is positive, in silicon-14. You have 10 core electrons, and so this is a core. And it has +4, because the 10 negative electrons and the 14 positive protons. And then the other electrons, the valence electrons, go in to make bonds. If this were a metal, the electrons, the valence electrons would be all over the place. And in the case of semiconductors, they'll go into bonds. That's the model, interacting atoms model, that people work with. So if you want to explain the properties of solids, you only have a limited number of particles, the electrons, the valence electrons, and the cores. You have electromagnetic interactions because weak interactions are too short range, too weak. strong interactions, too short range. So that's gravity's too weak. So you have that. You know quantum mechanics works, as I showed. But the problem here is that you have many, many particles, 10 to the 23rd particles per cubic centimeter. So you need approximations. Now, if you start working on trying to explain properties of solids, first thing you think of with a solid is you can't put your finger through it. You know, it's something, and you talk about hardness. And the first thing people did was scratch one thing on another and get the Mohs scale of hardness. And the chemical composition, depends what elements are there. And then X-ray came along, and you could X-ray everything, get the structure. But you could have two solids with the same structure, very different properties. So before you can really attack the first three, you have to explain this marvelous property of solids, is that the resistivity goes over 30 orders of magnitude. And the question is why? And why do we have semiconductors, metals, insulators, and so forth? And that's the key to finding out what's going on in solids. So to be more specific, these are the, let's say you have silver or bismuth or germanium or sulfur as being here it's conductivity instead of resistivity, the range. And Cattell had pointed out that this was a huge range. And here is a slide from Jim Chelikowski, who points out that the span in the order of magnitudes is equivalent to the size of our galaxy compared to the head of a pin. So it's a huge difference. So how does this happen, and how do we compute it? Well, you know for an atom, there are discrete energy levels. And if you put two atoms together, you'll have two levels, then more, for more out of three atoms. And then for many atoms, you get this. And so when you get to the solid, you have these allowed states of energy levels and forbidden area regions. And that forbidden region leads to the energy gap. So the spacing, when atoms get close enough together, the spacing is so small that it's continuous, quasi-continuous, and you get the gaps. So the answer to the age-old resistivity problem is that the gap, if the gap is bigger than 3 eV, you get insulators. You get diamond, for example, quartz. If the gap gets small enough, and let's say without doping, you get semiconductors, where the conductivity is temperature dependent. And if there's no gap at all, then you get something with a metal or a semi-metal. And this explanation basically was developed in the early days of condensed matter physics. But the models that people used, although they were wonderful for the time, they didn't distinguish between different materials. So the standard picture then was to take, let's say in the 20s and 30s, to assume that, for example, a metal was a box of free electrons, but quantum. And this is where the quantum metal came in. And then the background was positive with a compensating positive charge to make it neutral. And an enormous amount was learned. But the extension from that period to modern material science, for example, was difficult. And if you get a chance to look at the 1933 handbook article by Sommerfeld and Bethe, it's marvelous. It has almost all the concepts and things that you see in an undergraduate solid-state physics book. But it wasn't until much later that you could talk about real materials. And for example, Conyers-Herring pointed out that as late as 1960, the electronic properties of silicon, which was such an important material, was largely undetermined. But by 1965, you not only knew silicon, but you knew at least 14 semiconductors. So how did you get from one point to another? And again, it was more of an empirical or Gedanken or whatever model, like the Bohr model. The idea was that, and the idea went back to Fermi, actually, in the 1930s, and also Hellman. What Fermi wanted to explain was the properties of atoms that Amaldi and Segre had looked at, alkali atoms. And they excited the electrons far away from the core, and it went around. And so he wanted to calculate the optical properties. But then he said, I don't know the Italian words, he said, why do I need to know about all the core electrons? Why do I need to know about those? All I need to know is a potential that tells me what the electrons do far away. And that was a pseudopotential. So the idea here is that if you deal with that schematic picture of a solid, then what you want to know is how a valence electron, when it approaches the core, it's attracted because it's a Coulomb attraction. But when it gets near the core, there's a repulsive interaction because there's other electrons here. The Pauli principle pushes them out. So there's a Pauli force. So all the potential, pseudopotential, should look something like this. Attractive, and then turn around and come back. And the question is, how do you get this potential? Now we do it ab initio, and I'll show you. But at the time, at the beginning, the Bohr model kind of picture was you make a Fourier transform of the potential. So instead of V of R, you have V of Q. And because it's in a crystal, you have only specific, a few points where you need the Q's. So for example, if you want to tell what the whole band structure of silicon is, all the electronic properties, all you need is 3 numbers, these 3 numbers. And the way you get them is from experiment. You just fit one piece of data, and it fits everything. And these electronic band structures are as accurate as the most precise ones done today. In other words, if you take this empirical approach, you take the optical properties, and you fit band gaps, you only need 3 numbers, and it was a collaboration between theorists and experiments using the empirical pseudopotential method, meaning taking it from experiment. And also, you could focus on some very fundamental questions. So you could do dozens of semiconductors and get their electronic properties. And then that was applied, in talking about the applied area, for devices. So in Silicon Valley, they knew the electronic structure of silicon, or if they wanted to make an alloy, you could put them together. But the interesting thing about this is that if you did the electronic structure of gallium arsenide, you need 6 numbers because you have 2 atoms. With those 6 numbers, you could explain all the properties of gallium arsenide band structure. And then if you took the potential for the gallium out and put it into a gallium lattice, it would give you the properties of gallium. Same thing with arsenic. So from these empirical approaches, you learn that the potentials were transferable, many fundamental things. So this is just a commercial for empirical models. And in fact, I just chose one example. This is one where if you square the wave function, you get contours of where the electron is in the system. So here's 2 silicon cores, and these are electronic charge. And so the peak is at the center, and it goes down. And this experiment was done afterward, and it's very similar. In fact, the difference between 2 different experiments is the same size between experiment and theory. So that's from the empirical model. So then what do you do next? You say, now I want to do it from first principles. I just want to put in the atomic number. I want to get the potential. And that's following Fermi. You take a wave function, like a silicon wave function, and if the wave function for the atom looks like this, the dashed line, you go like this, and you have a potential that has to go to 0. And many people made up these potentials, and now we have potentials for the whole periodic table, pseudopotentials. And then you put them in a structure, and you can calculate properties. So this is a little complicated slide, but I'll just show you what you can do. If you take silicon atoms and you put them in the usual structure, diamond lattice, you add up the total energy, and you plot that total energy as a function of the volume. You just change the volume. Then for the usual silicon, which is diamond structure, you get a curve like this. And this is the minimum, and this is real silicon, and you can measure this point, and that gives you the lattice constant. And the curvature gives you the compressibility. Now, if you squeeze silicon, it will go into another structure, and that's a metallic structure, beta tin. And using this theory, you could predict all kinds of other structures of silicon. And then they were found afterward. So you can calculate the total energy and evaluate what happens as a function of pressure. And it's very precise. This was very early. This is the first one, just to give you some idea. If you compare the calculated lattice constant with experiment, it's within 4%, 0.4%, and the bulk modulus within 1%. Here's germanium and carbon. Anyway, calculations have been done, many on the same elements, but hundreds of materials have been looked at. Now, this is an interesting one because I want to come back to it later. Here are two special structures of silicon that you get at high pressure, theoretically. And so here's a total energy as a function of the volume. So the first one is diamond, the usual one, it's a semiconductor. We found that you could get a simple hexagonal one and a hexagonal close-packed one. And you could predict everything about them, including the fact that they're metals and superconductors. And fortunately, my colleagues in Grenoble were the first to show that they were superconducting, roughly where the theory is, and then it was a little refined, the experiment was refined, and you could show that you could predict superconductivity in a system that the system was not previously known, and you could make them. And so I'm going to use this later as an example. So the present state is that for a broad class of solids and clusters of molecules, and here I'm thinking of three-dimensional systems, you can use this plane wave pseudopotential method to give you the energies and the properties. All of these properties, structural and even excited state properties, using modifications like the so-called GW approach. You can also do optical properties. So in the 70s, this was not very popular. And I remember at a conference, I was asked why I spend time doing mindless research with a computer. And well, the only good quote I had was, I'm often asked whether doing physics research using computers is mindless research. My answer was that I can do mindless research without a computer. Now, times have changed. And nowadays, the approach is the standard model. So what I would say today is that this is the standard model, but some of it worries me because there are many people who, because the computers are so important, they become specialists on the computers, and sometimes they don't have those little empirical models. So that's why I'm making a big fuss about empirical models, that they should think about some of these things. And the other thing is that you can buy these programs, many of them, and sometimes people are using them who don't really understand them. But it's been an interesting area. So now that's the interacting atoms model. The elementary excitation model, where you probe a system and look at responses and look for emergence of new behavior. So for example, you're dealing with particles that explain what you're seeing, but they're not necessarily the kind of particles that you're used to. For example, one I'm sure you know about is that instead of, if you take one electron out of a system, instead of dealing with 10 to the 23rd minus 1, you deal with a hole. You make up this imaginary particle, which is the absence of an electron. And there are people in Silicon Valley who spend their whole career on this imaginary particle working with holes. But it's really an emergent concept. It's a quasi-particle. And you can't make holes going across the room here, but it gives you all the information you need. The same thing is for, now this would be a fermion, for bosons. So for example, you make the same analogy between light being a particle and a wave. And you say phonons are vibrations of atoms, and so you have waves, and you turn it into particles. So these are bosons. And so you're dealing with these so-called fictitious particles, but they explain all the properties that you need. So the idea that a new property can emerge, the idea of emergence, can be explained through some of these elementary excitations. So the concepts of emergence in condensed matter physics has influenced a lot of other areas of theoretical physics. For example, even the cosmologists and general relativity people are talking about space and time as not always being there, but an emergent property. And of course, we have examples like superconductivity is an emergent property, magnetism, quantum Hall effect, topological insulators. For example, let's look at the bottom one first. If you put on a magnetic field, I don't know why this isn't showing up, you get the quantum Hall effect. And that was one Nobel Prize. And then you also have the fractional quantum Hall effect. And there you have particles, quasi-particles of a third. And so you're explaining the properties in terms of fictitious particles. And now with topological insulators, we don't even need magnetic fields. For example, you have edge currents going around different directions, no magnetic fields. And this was, the whole idea of topological systems was the 2016 Nobel Prize. So let me just say a few words about nanoscience, and then I'll say a little bit about superconductivity and try to end on time. Now the success, one success of nanometer size scale is that, as I mentioned before, we're interested in the same size range as many other areas of science. The chemists and the biologists, I mean, here's a nanotube, we have DNA atoms, and so it really added a lot to breaking down the walls of universities, having chemists and physicists and biologists working together. And normally it was not happening. And then from a theoretical point of view, there's a couple of comments. First of all, although the properties on the nanoscale, like electronic, optical, magnetic, superconductivity, they're very different. But the methods that I showed you that work for three-dimensional systems work at the two-dimensional setting. And so the motivation for studying these, though, is that you get confinement. And when electrons are confined, they act differently. The reduced dimensionality gives you some really interesting effects, and I'll only mention a few, and the symmetry makes a big difference. So again, if you're going to explain experimental data and make predictions and applications, this is the other motivation. You have to be able to deal with these systems in such a way that you use the theory that was developed for 3D, and it works. So for example, we all know about graphene and all its many properties, but these are the kinds of pictures you can get nowadays where you can actually see the individual carbon atoms in graphene. And you can, because of they're done, these experiments are done with electrons bombarding, there are many oscillations and things, and we can calculate those things now. So one of the more interesting aspects of graphene is that if you look at a regular metal and you plot the energy versus a wave vector, it goes like the square. So the energy goes like the square of k, or energy goes to the square of momentum. And for a metal, the Fermi energy is here, so there's no gap, and you get excitations. For semiconductors, you have an occupied states, and then a gap, and then empty states. For graphene, or graphite, it's a semi-metal with no gap. And the energy dispersion is like a relativistic particle, where the energy squared goes like the momentum squared times c squared, so the energy goes linearly with the k vector, or the momentum. And so it looks like massless Dirac fermions with a speed, an effective speed that is 1/300th of the speed of light. And those properties allow you to do many things. Now, the first thing is, what about experimentally? And what I want to assure you is that this has been seen. So for angular resolved photoemission, you shine the light in, electrons pop out, and you can plot the band structure. So here's graphene doped with potassium, and for one doping and for another doping, and you can see this linear dispersion. And in fact, if you put in the many electron effects, the many body effects, and the self-energy, you can see that how the band velocity changes and everything. So the theory works for these materials. Let me mention just two things that we're waiting for final experimental verification. There's been some experiments, but if you take graphene and you decorate it so that it has lines across this way, you make a superlattice and shine electrons in, they all go in the same direction. No matter which way you put them in, they have no vertical velocity, and so you can colonnade electrons. And that's just because of the special nature of graphene. Also, if you take a piece of graphene, according to the theory, and just cut a ribbon, then on one side of the ribbon, the spins will be lined up, and the other side will be lined down. And if you put on an electric field, you can change that antiferromagnetic arrangement into a ferromagnetic arrangement. And so you can influence the spin with an electric field. Another thing that's popular now is to work on Weil semimetals, and I'll just tell you what that is. Here is a normal metal, where you have a valence band, a conduction band, and a gap. Here's a Dirac semimetal, where you have graphene, where you have linear dispersion, and there's no gap, and the Fermi level would be here, so you get something that's different. If you have two parts of the band structure connected in this way, you can show that this is a Weil semimetal and has interesting properties. People looked at these properties because they were interested in general relativity, and they were looking at other properties, and there are other node line semimetals, and so people are looking for these. But they usually look for them in heavy semiconductors and systems that have a large spin-orbit interaction. And what I want to tell you is that we can now show that you can make all of these with carbon lattices. So it's an interesting area of research. Now, for standard, if you roll the graphene into tubes, there are a lot of experiments you can do. If you roll graphene around so that you go 7 hexagons and move it up 1, that's a metal. If you go around 8 and don't move it up, that's a semiconductor. And if you put them together, and nature does this for you, you can get a defect with 5-fold and 7-fold rings, and this is a Schottky barrier. And these were predicted on the computer, and they've been found. Another thing is that instead of having carbon nanotubes, you have boron, nitrogen, and again, predicted on the computer, and we have them. And they're wide band gap semiconductors, which if you put an electric field on, you can make the gap get smaller. But unlike the carbon nanotubes, where you get a mixture of semiconductors and metals, these are all semiconductors. Okay, a little bit about superconductivity. I want to end with something quite new. Superconductivity, as you know, was discovered by Kamerlingh-Onnes. And there are many stories about whether he was there when it was discovered in 1911. And in 1911, this was in the spring, he discovered. In 1911, in the fall, they had this famous picture. And there's Kamerlingh-Onnes standing next to Einstein, and probably with a smile under the mustache. Everybody except Marie Curie and Jean's had some kind of facial hair. He told Einstein, and Einstein said that there would probably never be a theory of superconductivity. He felt that it was too complicated, molecular interactions and all the rest. And unfortunately, he died just before Bardeen, Cooper, Schrieffer came out with a theory of superconductivity for a broad class of superconductors. He would have liked that, I think. And so what happened was, after that, people wanted to raise the transition temperature, but it went up 1 degree every 3 years, a third of a degree a year, until the 1980s when it shot way up, copper oxide systems. And the highest temperatures for the last 15 years has been this material, around 165 K, and with some pressure. And then other materials came in. So the point was that up to this point, almost all of these superconductors are explainable by electron lattice interactions, class 1 superconductors. And the other ones, everybody has a theory, but there's no consensus. So the electron pairs are part of all theories, that the electrons pair. But in the BCS class 1, they're paired by the lattice interactions. And in class 2, they feel there's electron pairs, but there's no consensus on the mechanism. So the Solvay people got a large group of theorists together, and they gave us a week, and they told us to solve the problem of the copper oxide superconductors. And this was in the same hotel as the other picture with Einstein and Onus. And all week long, my theoretical colleagues were dressed, in the usual way. But for the picture, they got dressed up, as you saw. And people wanted to know where Einstein stood in the last picture and so forth. But then they were told, very disappointed, that it was a different room. Anyway, needless to say, by the end of the week, we didn't have a theory, and we still don't. But we still have conferences on how to go to room temperature. And some of the more famous conferences, one was in Norway, there was one at IBM, there was one in Leiden, and there are probably others, and even more recent, where people are trying to get to room temperature. And most of the time, the proposals are for these class 2 superconductors. But the problem is, for class 2 superconductors, since there's no consensus for the theory, you have to either look for some new mechanism besides phonons, maybe. Some people still think it's phonon. And you hope for new experiments. And the iron superconductors are very interesting, and they're giving interesting insight into the theory. But we still don't have a complete theory. But I was asking the question is, since we don't have a theory for type 2, we can understand class 1. And so the question is, how well can you predict things in class 1? And I already told you that we had a successful prediction of the metallic forms, lattice constants, all the properties of silicon at high pressure. And my former student had made the statement that perhaps silicon is the best understood superconductor, because you could start from first principles. So the question is, if you start from first principles, how high can you get in transition temperatures, and what's the best system? Well, this is an interesting formula. This is the hero of superconductivity for electron-phonon interactions. It's the strength of the lattice coupling to the electrons, electron lattice interactions, lambda. And if you let me put this omega squared down here, m omega squared, is a harmonic oscillator frequency. Okay? And so it's a spring constant. If I use the ionic mass and put this here, this would be the lattice spring constant. Eta is the electronic spring constant. It's the bonds, how strong the bonds are. So lambda, if you put it in that way, it's the electronic spring constant over the lattice spring constant. So to get the largest lambda, you want to have a small lattice spring constant and a large electronic spring constant. Now, the reason I wrote it this way, so lambda is the ratio of the spring constants, is if I take this quantity and I take the square root and I multiply by 0.2, that's the superconducting transition temperature. Okay? So it's a simple formula, but it tells you that you want strong bonds and like masses, and you would want systems where the bonds are strong, like in diamond. But the trouble with diamond is that you have no free carriers. So you need to get carriers into diamond. So we were pushing to try to get carriers into diamond. And the first experiments came from, so we want like masses and so forth, came from experiments in Russia. And they put boron in, and they got to 4 degrees. And then they and others put in more, and they got to 11 degrees. Then there have been rumors around the world that they had 25 degrees. I prepared this slide about a month ago, and I went out on a limb and said, I expect 30 to 50 degrees in the next couple of years. And fortunately, the day before I left for this talk that I was giving in Philadelphia, I got this email from North Carolina State University. And this is a man who worked with Q carbon, which I'll tell you what that is in a minute if you haven't seen the papers on it. And what he did was he said he got it superconducting to 36 Kelvin. And he said that it's being accepted for publication. And so I asked him to send me, this is Nayaran, to send me the resistivity. Here's the resistivity as a function of temperature. And you can see that it's fully superconducting at 36 Kelvin. And he did magnetic exclusion and so forth to show that it's superconducting. So the paper is now published, and it's, this is all I know about the details. You know, with superconductors, you have to be careful. But it's not unless if you do a heat capacity, then you know the whole thing is superconducting. If you do resistivity, it could be something else. But if you're at 36 degrees and there's only carbon and boron in there, it's still interesting. So Q carbon was discovered by Nayaran, and they make it by using high energy lasers, and I'm sure you have them here. And according to Wikipedia, it's easy to make. And you get the carbon into a molten form, and then you quench it very quickly. Now, it's clear I'm not an experimentalist, and so when I say it's easy, I only go by what they told me. And it seems to be amorphous, and it has a random structure with a mixture of sp2 and sp3 bonds. All I care about is how much boron they got in. And so in this particular phase, I had made some calculations and felt that they could get more boron in, and they have. And so now they have quite a bit of boron in. Now, I just got an email here that they're up to 57 degrees. So where is the theory on this? Well, when we worked on it, we got for a diamond, if you could get the density of states, if you can get enough boron in and get the peak at the proper place, you could get 290 Kelvin. At the time, it was 10 degrees. Graphite is a little trickier, but is also in that range. And boron nitride and silicon, using that formula, if you can dope, this is where you get. So I have to warn you that predicting is difficult, especially about the future. And that's from our philosopher, Yogi Berra. And also, I go back to Einstein, that the most valuable tool of the theoretical physicist is his wastebasket. Okay, thank you very much.
Thank you very much, Professor Cohen, for this very nice talk. Are there questions in the audience? Okay, so I have a question. So you told us that it seems that the difficulty is in doping, right? So what are the typical numbers that are necessary to reach those 290 Kelvin? In the
20–30% range, you should start getting higher transition temperatures. And I think they may be close to that here.
And isn't there any problem of aggregations of the borons, or the density structure is destroyed in the process? Or?
Well, there's no structure here. That's the thing with the Q carbon. The reason I was interested in is I didn't think that the boron would disrupt it that much.
Okay.
But getting boron in is difficult. So the kinds of things that people tried is to try to get the boron in a layer in the surface. And you can show, first of all, that if you cleave diamond and then one direction, you'll get all kinds of dangling bonds. And if you want to make that surface really hard, you put boron on top, and the boron sits there. And that's probably, except for graphite or graphene, probably the strongest bond around on top. But then if you try to get enough in, it's very hard. So people in Australia have been doing ion implantation, and they're getting layers of boron below the surface. Now, if you went to nitrogen, then you'd have an N-type diamond, and that might be even more interesting, but I haven't seen any experiments on that.
Okay.
So it's all been boron-doped P.
And isn't there any phenomenon in the surface if you try to push the borons in the carbon? Then so you told us that there is this very strong surface, and isn't the surface interesting by itself? Or?
I would think so, but it's not, but so far the layers that they're getting of boron in carbon have not given superconductivity, and I don't know how the experiments in Russia are going or how they're doing it, and there's a Japanese group doing it. But this Q carbon is a breakthrough, but I have not seen the latest data. You know, I'm just telling you what they're telling me, but I haven't seen it. And as you know, in superconductivity, people have claimed many high-temperature superconductors that have not worked, but that's the situation right now.
Thank you very much, Professor Cohen. Small question.
Just about the fact that you were looking at overpressure, change of the lattice constant and so on. What about Jupiter, the planet? Supposed to be hydrogen, the core,
yes,
and extra pressure, which makes it metallic or even superconductive metallic state, yeah, like in alkali, which is hydrogen metallic, same.
Yeah.
Is it something new? Because it was an idea a long time ago.
Yeah. Well, the thing is, it was an old idea, but people worked on it all these years. The problem is that when you, for theory, when we compress hydrogen, the first thing is we get an insulator, okay, depending on structure. Then we compress it further. The question is whether or not we're getting a semi-metal where the conduction bands and valence band overlap each other. And so we look at that. And we also looked at what happens when you go all the way, like in the alkali metals, and it becomes a straight metal. The trouble with the theories, most, as far as I see, is that we don't know the structure. And we haven't been able to figure out what the structure would be as you get the higher and higher pressures. Now, there's some controversial experiments now that they actually have seen metallic hydrogen under pressure. But it's not universally accepted, and it's probably has some problems. So first we have to make it a metal. But once it's a metal, from a theoretical point of view, it should be superconducting. And on Jupiter, even if it's not in a solid state, even if it's just a liquid, it should be superconducting. And the transition temperatures are expected to be high because the atoms are so light that even if you use this formula, the mass is so light that it gives you a very high Debye temperature, and that gives you a high superconducting temperature. So Jupiter is probably superconducting, which means that it would trap magnetic fields. And they see magnetic fields, but the fundamental theory is still being worked on.
Thank you very much again, Professor Cohen, for coming.
Thank you.